Locate critical points using derivatives. Alright folks, in this lesson we're going to be discussing maximum and minimum values. But before we dive into that, we need to just get some vocabulary cleared up, make sure that we're all on the same page as we will be introducing some new terminology here. So we've talked about maximum values and minimum values, and we're adding a new version of those words here, maxima and minima, and those are just the plural forms for maximum and minimum. So if we have more than one maximum, they would be referred to as maxima, and if we would have more than one minimum value, they would be referred to as minima. Now, together, maximum and minimum values also have kind of an umbrella term, which is extremum. So extremum is just talking about the extreme values of a function, being the maximum and the minimum. But mathematicians, we're a little bit lazy, so we would rather use one word instead of having to use two. So instead of saying find the maximum and minimum values of this function, we could just say find the extremum. Nice and simple. And then finally, we have the plural version of extremum, which is extrema. So extrema just represents the maxima and the minima of a particular function. So again, most of these are words we know. We're just adding different versions of them being the plural forms. Alright, so then the question that needs to be asked is, how many types of extrema are there? Well, as it turns out, there are two types of extrema. There is the absolute or the global extrema. They both use the same thing, but they kind of explain the extrema in a different context. So both of these terms are used. They're used interchangeably, so we will need to know both of them. And then we also have local/relative extrema. Again, same thing. They both explain extrema a little bit different ways, but they both represent the same thing, and they are both interchangeable vocabulary words. Alright, so we're going to start off with looking at local/relative extrema. So, if we dive back into some of our pre-calculus knowledge, we know that maxima and minima can exist at peaks and valleys. So if we were to look at this particular function here, hopefully we can see that we would have two minimum values at these different valleys right here. So we would have a minimum and a minimum, and then we can see that we can have a maximum value here at x equals 2. Now let's remember, we cannot have a maximum value here or a maximum value there, because these arrows mean the function is going up forever and ever and ever, and if our function is continually going up, it's never going to stop, so therefore it can't have a maximum at those 2 points. So please don't fall into that trap and think, oh, the maximum is just the highest point, which that's good enough for pre-calculus, but now that we're in calculus, we can't use that kind of loose definition. Alright, so in addition to peaks and valleys, we also know that we can have maxima or minima at corners or cusps. So if we look at this particular function, we can see that we have a peak here. So we'd have a maximum value. We can see that we have a valley here. So we'd have a minimum. And then finally, we have a peak. And since this is kind of an upward mountaintop peak, this would be a maximum value. So great. We can identify maxima and minima on graphs. But just because we can find them doesn't mean that we have properly defined them yet. So let's go ahead and let's look at defining them. So one way that we can find them is that local or relative extrema are called, or let me start that slide over. Alright, so these maxima and minima are called local or relative extrema since they are the highest or their lowest point in their general or local area. What do I mean by that? Well, if we look at this particular function, we have two peaks. We have a peak right here, and we have a peak right here. And based on our loose definition, these would both be maximum values. However, maximum typically implies the highest point, and we can see that at x equals -3, that maximum has a higher y value than at x equals around 1. So how can both of these be maximum values if one is significantly higher than the other? And that's where this whole local or relative term comes into play. So when we're talking about local, we're talking about it being the highest point locally. So if we wanted to, we can kind of draw a little neighborhood here of where just a group of our x values live. And we can say that based in this little localized neighborhood, this little localized area, that this particular point would be a local max, because it's the highest point in that little neighborhood. And similarly, we can draw a little neighborhood here around our other maximum value. And when we compare it to all the other points that surround it, again, in that little highlighted neighborhood, it is relatively the highest point. Because if you compare it to all the other y values in that little area, it's the highest. So that's why we call it the local or the relative extrema. And then same thing is true for the minimum values. We can see that we're going to have a minimum value here and a minimum value here. And these are the minimum values for the same reason. We can draw a little localized neighborhood around that valley, and we can see that based on all the other y values in that little highlighted area, this is the lowest one, or the minimum. And then similar thing over here. Again, relative to all the other points in this shaded green area, the y value at x equals 3 is the lowest, is the minimum value relative to all the other y values. So that's where this vocabulary comes from, why we call it local and relative. Again, it's just the way that you're framing it to understand it, local versus relative, but they both mean the same thing. Alright, so saying that extrema exist at peaks, valleys, corners, and cusps is fine when we were in, pre-calculus. But now, after 2 units of calculus, it's time for a better definition. We can do better than just saying, oh, it's the highest or it's the lowest points. Because again, we know all about limits. We know all about derivatives, rates of change, tangent lines, slope, all kinds of stuff now. So we can put that to, I'm going to say good use, but you folks at home might disagree with that fact, but definitely good use. Alright, so let's start with examining peaks and valleys. Because again, we know that's where the maximums are. But how can we define it better than just saying the highest and lowest points? So, if we take a look, and that's not what I wanted to do, clicked the wrong one. Alright, let's see if I can get the right one here. We know that there's, I can't get it. Okay, so we'll just kidding. All right, let's start this all over. Come on, cool one. Do better. Anyways, all right. So we know that at peaks and valleys there exist turning points. We also know that at turning points we are going to have a horizontal tangent line. So we can see here that we can draw said horizontal tangent line through the peak and through the valley. And we also know that since we have horizontal tangent lines, the slope of a horizontal line is 0. So therefore the slope of all these tangent lines is 0. And now slope, that should be, setting off a bunch of alarm bells in our heads, because we've been talking about slope for a couple weeks now, and we were supposed to make the connection, well, slope is rate of change is, ta-da, the derivative. So, we know that since horizontal tangent lines have a slope that is equal to 0, we know that at these points, the derivative will also equal 0, because the slope of the tangent line is 0, because it's horizontal. boom, boom, boom. So therefore, we can then make the connection and say that local extrema can exist where the derivative is 0. Now, I want to just point out one super important word here, and that is the word can. So local extrema can exist where the derivative is 0. It doesn't say local extrema will exist. So now we'll dive into that a little bit later on, but for right now, please emphasize the word can. So just because the derivative equals 0 doesn't mean there will be a local extrema. It means there can. We'll have to do a little bit more investigating there. Alright, so we did peaks and valleys. We also know that maximums and minimums can exist at corners and cusps. So let's talk about corners and cusps. So we know corners and cusps exist at a quick change of direction. Because obviously here at x equals 2, if we approach 2 from the left-hand side, we are increasing. And then all of a sudden at x equals 2, we pop the other way, and all of a sudden we are now decreasing. And when we were examining corners and cusps, we said that at a corner or cusp, we are going to have a vertical tangent line. And if we can think back from Algebra 1, Algebra 2, pre-calculus, or even earlier in the semester, we know that vertical lines have an undefined slope. And now, since we know that slope is derivative, when the slope is undefined, that means the derivative is also undefined. Which means we can then make the conclusion that local extrema can exist where the derivative is undefined. And there's that word again. Local extrema can exist. Again, this does not guarantee there will be a local extrema where the derivative is undefined. It just means there can be. And we'll have to do a little bit more detective work and investigating when we get there. Alright, so now we can put these two thoughts together, and we can say that local extrema, there's that word can again, local extrema can exist where the derivative is equal to 0 or is undefined. Boom, combined together. Now, although these x values, or where these points would have a 0 or undefined slope, may or may not be local extrema, we do have a name for these points. So these points, where the derivative is equal to 0 or undefined, is known as a critical point. Depending on what textbook or source you use, you might also hear the word critical number. I might use them interchangeably, so please know critical point and critical number represents the same thing. I've just read so many textbooks over the years, I have pulled both of those vocabulary terms into my everyday vernacular. Alright, so let's define critical points a little bit better. So critical points, we're going to let C be a point on the inside of the domain. So C is an x value in the domain. We can say that C is a critical point if the derivative at x equals C is 0, or if the derivative at x equals C is undefined. And that is huge news. Not quite yet, but it's going to become huge news for a lot of what we're doing in Unit 3. Is being able to find these critical points are going to become so important for this unit. With that being said, let's take a look at some examples. Alright, so here, nice simple example. We want to find the critical points for f of x equals 2x squared plus x plus 2. Now, we're looking for the critical points. And as we had just talked about in the last slide, we know that critical points are when our derivative, f prime of c, is going to equal 0, or where f prime of c is undefined. So, probably the first thing we should do is find the derivative. So, we can come in here, we can take the derivative of our function. F prime of x is going to be 4x plus 1. Alright, well, 4x plus 1 we know is a linear function. And we know linear functions exist everywhere, because a linear function is a polynomial, therefore it exists everywhere. So since it exists everywhere, we know the derivative will never be undefined, so that means we just need to check for when the derivative will equal 0. So that means I can set f prime equal to 0, so I get 0 is equal to 4x plus 1, and then I can solve for x, and I get x is equal to negative 1/4. And x equals negative 1/4 are the critical points to the function 2x squared plus x plus 2. Alright, next up. We want to find the critical points for f of x equals x squared times the natural log of x. Whew. Alright, here we go. So, we want to find the critical points, which, as we just talked about in the last slide, means we first need to take the derivative. But, unfortunately, product rule, x squared times the natural log of x. So when we take the derivative, we're going to have to use the product rule. Product rule says take the derivative of the first term, which is 2x. We multiply it by the second term, which is the natural log of x, plus the first term, which is x squared, times the derivative of natural log of x. Remember, derivative of natural log is 1 over the inside, times the derivative of the inside, and the derivative of x is just 1. And then we can come in, we can continue simplifying this down. So let's see, we'll get 2x times the natural log of x plus x squared over x, which we continue simplifying down. F prime of x is equal to 2x times the natural log of x plus x. Alright, now here we have 2x times the natural log of x plus x. This is a function that is going to exist everywhere, which means we just need to set the derivative equal to 0. So, we'll have 0 is equal to 2x times the natural log of x plus x. Alright, so now how do we go about solving this particular equation? Well, we can start off by looking at the greatest common factor. We can see that both of our terms have an x. So I can go ahead and I can factor out that x, which will leave us with 2 times the natural log of x plus 1. And then we know, based on the zero product property from way back when, if we have two things being multiplied together to equal 0, we can set each of the factors equal to 0. Alright, so I just found my first critical number, which is x equals 0. Excuse me, critical point. I just did it. Alright, so then for 2 times the natural log of x plus x equals 0. And it's not plus x. What are you doing, Coolman? Go away, go away, go away. Alright, we'll start over. Alright, x equals 0, critical point. And then we have 2 times the natural log of x plus 1 equals 0. And then to solve an equation that has a natural logarithm in it, we want to get the natural log by itself, which when we do that, we'll get the natural log of x is equal to negative 1/2 power. And if we remember back from pre-calculus, we know to undo a natural log, we'll need to take the inverse, which is the e function. But what we do to one side, we have to do to the other. So the e and the natural log will cancel out, leaving us with x is equal to e to the negative 1/2 power. So there we go. We just found all of our critical points for the function x squared times the natural log of x. Next up, let's take a look at finding the critical points for f of x equals the square root of x squared minus 16. Now, for this one, the first thing we're going to have to do is we're going to have to get rid of the square root because there's no derivative formula for finding the derivative of radicals. So that means I can first start off by rewriting this as x squared minus 16 to the 1/2 power. Now, when we take the derivative of this, we do notice we have a function inside of another function. So we are going to have to use the chain rule. Chain rule says we take the derivative to the outside, so 1/2 times the inside raised to the negative 1/2 power. We're going to leave the inside alone and then multiply by the derivative of the inside. Alright, then from here we continue to simplify this down. So we'll have f prime of x is equal to, let's see, I can simplify this down to be 2x over 2 times x squared minus 16 to the 1/2 power. And let's see, I have a factor of 2 in the numerator, factor of 2 in the denominator I can cancel out, leaving me with f of x is equal to x over. And for the purposes of what we're going to do next, I actually want to put the x squared minus 16 back in the radical. So I'm going to change the 1/2 power back into a radical, and hopefully you'll understand why in just a moment. But that's going to give us a derivative of x over the square root of x squared minus 16. Now, we know that critical points exist when the derivative equals 0, or where the derivative is undefined. Since our derivative is a fraction, our derivative is going to equal 0 when the numerator of a fraction is 0. So therefore, to determine when the derivative is 0, we'll just take the numerator, x, and set it equal to 0. And there you go, boom, critical point. And then we have to figure out when f of x is undefined. And we know a fraction is undefined when the denominator is equal to 0. So therefore, we can set the square root of x squared minus 16 equal to 0. And now we just need to solve this equation. So we'll get rid of the square root first, square both sides, boom, 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 leaving us with x squared minus 16 equals 0. We can add 16 to both sides, x squared equals 16. Then we need to get rid of the squared, so we'll take the square root, boom, 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 and we'll end up with x is equal to plus or minus 4. And there we'd have it. We have 3 critical points for the function the square root of x squared minus 16. So, does a critical point guarantee that there is going to be a local max or local min? And the answer is no, because the way that we defined it is that there can be a local max or local min at a critical point. So let's dive into that and figure out when a critical point is a local max or when it is a local min. Alright, so we know that we have a critical point in 2 situations. When the derivative is equal to 0, or when the derivative is undefined. Well, we know that when the derivative equals 0, that means the tangent line is 0, or excuse me, that means the slope of the tangent line is 0. And we know that the specific type of tangent line that has a slope of 0 is a horizontal tangent line. And again, we looked at graphs that had maximum and minimum values, and we know that horizontal tangent lines live there, which is why we said critical or maximum minimums can exist at horizontal tangent lines. However, that's true, but then there's that oddball circumstance out there when we just have this momentarily pause and we create this kind of ledge in the graph that has a horizontal tangent line. And we can see that in this case, there isn't a turning point. So we do have the horizontal tangent, but there is no turning point here, which means there's no local extrema. So yes, when the derivative equals 0, that means we have a critical point, and that critical point can mean it's local max or min, but because we have this situation where we have a horizontal tangent line, but we don't have a turning point, means that that's not always true. And similarly, just because the derivative is undefined doesn't guarantee we're going to have a local max or min. And again, the one that we looked at was when we have a corner or a cusp, and there's a vertical tangent line. Boom, max or min. But we also know that we can have the slope being so steep that it creates a vertical tangent line. And unfortunately, at this vertical tangent line, there is no corner or cusp, which sadly means there are no local extrema. Alright, so that's the reason why we say critical points can be local maxes and mins, but they are not guaranteed to be local maxes and mins. Alright, so let's just try to make this a little bit more clear, but also possibly a little bit more confusing at the same time. So, we know that all local extremas have to be critical points, because you can't have a max or min without there being a horizontal tangent line or a vertical tangent line. However, as we just pointed out with those two situations, just because they're the critical point doesn't mean that they are local extrema. So, local extrema are critical points, but critical points are not necessarily local extrema. Alright folks, that is all for locating critical points using derivatives.